Dear students, so in this we are going to see about the least disk apparatus. The aim of this experiment is to find the coefficient of thermal combustion of a conductivity of a bad conductor using least disk. So these are the apparatus required. We need least disk, metallic disk, and we need a steamer. We need a bad conductor, either glass or mica. And here is the formula. This is the figure. So you have a steam chamber, you have a good conductor in between, and you have a brass disc, and between you have to place a sample disc, either mica or glass. And this one is the formula. Thermal conductivity is equal to M into C dt by dt, or dt by dx is divided by 8 t2 minus t1 divided by x, where dt by dt is the rate of cooling, m is the mass of the brass disc, c is the specific heat capacity, a is the area of the sample, k is the coefficient of thermal conductivity, x is the thickness of the sample, and m is the mass of the metallic disc. So by using this formula we can able to calculate the thermal conductivity of the bad conductor. Okay, now so what we are going to observe is rate of cooling. Okay, so when the temperature decreases, what is the time, how much it is, how much time takes to decrease the, when the temperature decreases, how much the time taking, so that we are going to note. Okay, so what is the time for 70 degree, what is the time for 68 degree, what is the time for 64 degree, what is the time for 62 degree, like that we are going to see the rate of cooling, and we are going to draw the graph between time and temperature. So by and we are going to determine, by using the slope, we are going to determine dt by dt, where small t is the time, capital T is the temperature, and if we substitute this in the formula, we'll get the thermal conductivity, coefficient of thermal conductivity. I'll show how to do it in the simulator. So now you can see this one is the steam chamber, this one is the brass disc, this is also a lease disc, and this one is the thermometer T1, thermometer T2. Here this one is the tube, so that the steam will pass from steam chamber to the steam chamber. This one is the steam generator. So now I'm going to click the specific heat capacity of the metallic disc is 910, thermal conductivity of the metallic disc is 250, mass is 0.1. So now least disc, I'm going to select a material. So I'm going to select here aluminium. Least disc height, I'm going to select, just see here it is changing. I'm going to select as 2. Okay, and the least disc radius I'm going to select as, I'm going to keep it as 4 centimeter itself, and I'm going to select the insulator, either mica or cardboard. So I'm going to select the cardboard, and thickness of the cardboard 1.1 millimeter. I'm going to place the insulator. Now just see, insulator is placed. Now I'm going to start the steam, so that what will happen, the steam will generate the steam generator will generate the steam, and it will pass through this, and it will go to the steam chamber, so that the temperature will get raised. Here you have an insulator, so the temperature in the least disc comparatively rise slowly than the steam chamber. Okay, because of the insulator, we have insulated, where inserted the insulator in between this disc and this least disc. Okay, so just you can see the comparatively the T1 temperature is higher than T2 temperature. Okay, at one point both the temperature become constant. Okay, and we have to stop the steam chamber at that, and we have to remove the cord. We have to know the rate of cooling by using the rate of cooling of thermometer 2, and we have to know the time by using this stopwatch. So the temperature is rising. You can see that comparative temperature rising. T2 is rising slowly, T1 is rising vigorously because it is in direct contact with the steam chamber. Now we can, if you want, you can note all the years: aluminum lease disc, mass of the lease disc, radius, thickness of the insulator, everything it is given. T1, T2 degrees Celsius. Now we are going to note that. See, now the constant temperature reached, and we have to note the temperature. T1 is 100 degrees Celsius, so you have to note the 100 degrees Celsius over here. T2 is 68 degrees Celsius, and we have to note the 68.72 degrees Celsius. We have to note here. And now I'm just removing the insulator. And I'm stop steaming. So now just see, the temperature is getting down, and we have to start the timing, and we have to note the temperature over here, temperature and timing over here. If you put show graph, it will show you the graph. See the graph. Okay, so the temperature is decreasing, now the time is increasing, and you have to note the rate of cooling. Now the graph is see, the graph is generated between time and temperature. From the graph we have to note dt by dt. From that dt we have to know the slope value, and we are going to calculate the thermal coefficient of bad conductor, thermal conductivity of bad conductor. So this is enough. I'm going to stop here. Okay. Now see this graph. We have to plot the graph dt by dx by dt by. From the graph we have to find dt by dt. So from that we have to substitute that in this formula. We know the mass, we know the specific heat capacity. By using the slope we have to find dt by dx dt, and we know the x, so substitute all this here. H is the height of the lease disc. Substitute all this formula over here, substitute all this values in this formula, so that we will get the coefficient of thermal capacity, thermal conductivity of the given material. What material we have used? We have used cardboard. Okay, thank you.